you homework, okay? So we're on page 893, right? And what we're doing here is we're supposed to be doing the practice problems 1, 2, 3, and 4. Is everybody good so far? Hello, Raymond. How are you, baby? I'm doing great.
I was called to the front office and they sent me to JRTC, and I was talking to recruiters.
No problem. You got your lunch though, right? Praise God. Okay. So, first things first, when we're drawing a free body diagram, what are the steps that we have to do? Do you remember what they are?
You said free body diagram?
Free body diagram. What do we have to do?
We have to draw a picture?
Yep. The first thing we're going to do is draw a picture. What is the second thing we got to do?
Identify the system.
Identify the system. Okay. What's the next thing we're going to do? Draw the vectors. And then what is the last thing? Net force. Look at y'all. Y'all are fabulous. Okay, so let's look at the very first one. The very first one says the skydiver falls downward through the air with a constant velocity. The air exerted on the upward force on the person. So the first thing we're going to do is draw a picture of our skydiver. Okay, so here is our skydiver.
Yeah.
Okay, so then the next thing we're going to do is we're going to identify our system. What is our system? The skydiver, right? We're going to put us a dot in the middle, and I like to draw my vectors separately so that I can see it instead of on top of the picture. So, now if he's falling out of the sky, what is pulling him down? Okay. Force gravity on the skydiver by the earth. Do you remember that list of ones that we used yesterday? Remember the ones we wrote down yesterday of the different types of forces? We're going to try to use those today.
What's that?
That's what we draw.
Force gravity on the skydiver by the earth. It's okay. So what is the other force here? Air resistance, right? And remember, we have air resistance. So we're going to do force, air, on the skydiver by the air. Okay? Anything else that we need?
This is fairly.
Now, the question that I have for you is your arrow going down to gravity, is it longer than the air force? Yes, because he's falling, right? So if it was a balance force, what would we do? We would draw an arrow, and then we would draw a line in between those, right? But we don't. So the only thing we have left to do is decide what the net force is, correct? So what is our net force for this? Which one's longer? They're in the two different directions. What do? You subtract the two.
Yeah.
So my net force is going downward. That's all you got to do. How's everybody so far? Okay. I want you to look at number 2. And we are on page Raymond 93. And you're going to read that one and you're going to try to draw it yourself. And then we're going to do it together. Okay? So go ahead. I'll get it. Thank you, Grayson, though. It's sweet of you. Oh, she cried. How you doing, sweetheart? We're going over the practice problems. Go ahead and get your textbook. I think it's back there. Or is it up front? Oh, let me just grab you a book. I just like whatever you feel like you need to draw, baby.
This is already.
Okay, so you're doing question number 2 now, guys. Ladies that just got here, draw this. This is the first one of the questions from today. We're on page 93. Ma'am. Okay, so number 2 says, you hold a softball in the palm of your hand and you toss it up. Draw the diagram while the ball is still touching your hand. So, first thing we're going to do, I think I got 5 fingers. All right, so I have my hand, right? I have my softball, right, in my hand. What object is going to identify our system? What system are we using? The ball or the hand? The ball, right? Okay, so draw you a little circle around it. Next thing we're going to do is we're going to put our dot. This dot right here represents this ball, right, guys? Now, let's think about the ones that we used yesterday. What force is going down? Okay? Correct. So it's force gravity on the softball by the earth. Okay? Is the ball sitting still right now at this moment?
No.
It's in your hand, but is it sitting still? You hold a softball in the palm of your hand. So yes, it's sitting still, right? Now, what force is going up? Now, what force is always the opposite of gravity of something standing still? Not tension. Not applied. Not friction. Normal force. There we go. Force, normal, on the softball by the hand. Because that's what's touching it, right?
Yeah.
Remember the example yesterday? We were talking about a ball being on a desk, right?
Yes.
And that was the table that was holding it up. Now, what else do I need to do to this right here? Draw lines in between. Very good, ma'am. I like that. And then I need to identify my force net, right? What is my force net? It's going to be 0.
Yeah.
There's no force net at all. So when we're talking about force net, we're talking about what direction it goes or an amount. Same thing. It's okay. Either one you want to use. You can do net force, which I did there, right, baby? And I did force net over here. They're both the same thing. Is everybody good with number 2? All right, go ahead and start doing number 3. It says after the softball leaves the hand, it rises and slowing down. So we got the hand this time, but this time the softball is being tossed in the air and it is slowing down. Based on what we know so far, what is happening to the softball? So when you first throw the ball up in the air, the force applied is greater than the force gravity, right? And as it goes up in the air, the force gravity and the force applied is starting to equal, correct? When it gets to the very top, what is happening through the force applied? Has nothing. Only thing that it is that it's the force gravity that's pulling it down, right, guys? So at this moment, what's going on with the ball? Is it reaching the top? Is it at the very top of how much force applied is? And is it getting ready to come back down? Does everybody agree? Okay. So based on that, what am I going to draw?
Down, an arrow pointing down for the force of gravity on a softball or and another one going up would be
Has it stopped? Has the ball stopped? What does the thing say? Has it stopped or is it going to stop?
slowing down.
Slowing down. There's your key. Force what?
Force applied.
Force applied. Remember that's APP, right?
Yeah.
On the softball
By
by the
the hand.
hand again. All right? What's my net force?
Would it be the force applied so greater because it's slowing down? It has to.
Here's the thing. Now, do you agree? And I see where your logic is. But do you agree it's running out of steam here?
Yeah.
Right? If it's running out of steam here, does it not make sense to you that gravity is more of a force? So my net force is which direction? Down. Big arrow, small arrow. Good, everyone? Okay, let's go ahead and see what's going on with number 4. After the softball reaches the maximum height, it falls down, speeding up. So what's going on here? Is the hand involved? It's the softball by itself. Softball's my system, right? So it's saying it's speeding up, correct? So what forces are involved here?
Gravity. Normal.
Anything else?
Air resistance.
Nothing. Does it say air resistance? It just says that after the softball reaches maximum height, it falls down, speeding up. Now, Raymond, good question. If it was not speeding up, but it was slowing down, what would be happening? Air resistance. Got it? So what's my force net? Going down. Everybody good? Does everybody understand? Are you feeling better about these types of arrows and all these different types of forces? Good? Okay, so now what we're going to do is go ahead and turn to your next page, which is page 94. We're going to start our one-pager now. We're going to turn in our book to the next page. We're going to start our one-pager now. That math was the homework, yes, sir. That was, but this is what it is, all right? If you did it today, leave it on that page. Draw you a line underneath that and do your one-pager underneath that. Because we did it today, correct? Okay. Is everybody ready? Where'd you get it?
Acceleration and force. To explore how forces affect an object's motion, think about doing a series of investigations. Consider the simple situation shown in the top photo of Figure 5, in which we exert one force horizontally on an object. Starting with the horizontal direction is helpful because gravity does not act horizontally. To reduce complications resulting from the object rubbing against the surface, the investigations should be done on a smooth surface, such as a well-polished table. We'll also use a cart with wheels that spin easily. Apply constant force. How can you exert a constant unbalanced force? One way is to use a device called a spring scale. Inside the scale is a spring that stretches proportionally to the magnitude of the applied force. The front of the scale is calibrated to read the force in newtons. If you pull on the scale so that the reading on the front stays constant, the applied force is constant. The top photo in Figure 5 shows a spring scale pulling a low-resistance cart with a constant unbalanced force. If you perform this investigation and measure the cart's velocity for a period of time, you could construct a graph like the green line shown in the velocity time graphs for constant forces in the middle panel of Figure 5. The constant slope of the line in the velocity time graph indicates the cart's velocity increases at a constant rate. The constant rate of change of velocity means the acceleration is constant. This constant acceleration is a result of the constant unbalanced force applied by the spring scale to the cart. How does the acceleration depend on the force? Repeat the investigation with a larger constant force, then repeat it again with an even greater force. For each force, plot a velocity time graph like the red and blue lines in the middle panel of Figure 5. Recall that the line's slope is the cart's acceleration. Calculate the slope of each line and plot the results for each force to make an acceleration force graph, as shown in the bottom panel of Figure 5. The graph indicates the relationship between force and acceleration is linear. Because the relationship is linear, you can apply the equation for a straight line, y equals kx plus b. The y-intercept is 0, so the linear equation simplifies to y equals kx. The y variable is acceleration, and the x variable is force, so acceleration equals the slope of the line times the applied net force. Figure 5. A spring scale exerts a constant unbalanced force on the cart. Repeating the investigation with different forces produces velocity time graphs with different slopes.
Okay, so cart, right? Car. This right here is what's called a spring scale, okay? Our spring scales, we have different ones. The ones that you want to use is the ones that have newtons, okay? So in this experiment, what they did is they took the car, they took their spring scale, and they pulled it across the table, and it had constant force. How do you know that? When you pull the spring scale down, it shows you how many newtons of force that you have. Now let's think about this logically. If you had a spring scale and you had a car and you were pulling it up the ramp that we have out there, what do you think is happening to the force? Are you having to exert more force as it goes up the ramp? And then when it comes down the ramp, what happens? Okay, so when you're taking the car, because this is very important because you're going to be doing this tomorrow, okay? When you take the car and you're pulling it up, you're going to pull it up this way, okay? When your car is going down the ramp, you're going to hook it up to the back, all right? So here's the front of your car, up the ramp, goes this way. When you're going down the ramp, you're going to go and use it the other direction. Do you understand what it's talking about here with graphing that? When you're graphing that, what are you going to be graphing? What is your axis? What is the names of them? What does this say on here?
Velocity.
It says velocity versus time. Okay? So how do we find the velocity of how fast the car is going? How would we do that? Depends on the slope. We have some photo gates back there that you're going to be using, okay, to find the velocity. So, let me explain that also. So, on our track that we have, I'm going to bring it up. I got mainly hooked up. I don't think we can do it on that. So, this is the track you're going to be using tomorrow, okay? So what you're going to have to do is you're going to have to assemble your track. So you're going to have the ring stand, you're going to have the car, and you're going to have your photo gates. Now in physical science, did you use this? Some of you did, some of you didn't. Okay? So when you're trying to find out how fast or the velocity is, Those of you who've used it before, how do you do that? How do you find the velocity if you're using your car? It's meters per second. So let's think about how do we find meters per second here? Well, our meters are here, right? So to find our velocity, we would have to use the beginning and the ending, right? Subtract those, right? And then also, for us to get the time, our little timer that we have on here is going to show us that. And on here, you're going to go through, and it's going to tell you how long it has been, okay? So tomorrow, when you're going and you're taking your car down the ramp, and you're using this, right? You're sliding it down. This turns the photo gate on. This turns the photo gate off. This tells you the time from here to here, right? The distance is marked with a ruler on the side so that you would know what the distance traveled is, correct? What does this tell us?
Yes.
The force. So when you're doing a force diagram. Just saying this really quickly today because tomorrow when we do our rotations, you're going to be in lab longer than you normally are. Does anybody have any questions about the lab for tomorrow so far? Okay, let's go ahead and go to the next page. Is there anything that you wrote in your notes for that? You already know slope. You already know X and Y axis. You already know velocity time graphs. Pretty much everything, correct? Okay, let's go to the next page.
Interpreting slope. What is the physical meaning of the slope of the acceleration force graph? Does it describe something about the object that is accelerating? To see, change the object. Suppose that a second identical cart is placed on top of the first, and then a third cart is added as in figure 6. The spring scale would be pulling 2 carts and then 3. A plot of the force versus acceleration for 1, 2, and 3 carts is shown in the graph in figure 6. The graph shows that if the same force is applied in each case, the acceleration of 2 carts is 1/2 the acceleration of 1 cart, and the acceleration of 3 carts is 1/3 the acceleration of 1 cart. This means that as the number of carts increases, the acceleration decreases. In other words, a greater force is needed to produce the same acceleration. The slopes of the lines in figure 6 depend upon the number of carts. That is, the slope depends on the total mass of the carts. In fact, the slope is the reciprocal of the mass, slope equals 1 over mass. Using this value for slope, the mathematical equation y equals kx becomes the physics equation A equals F net over m. What information is contained in the equation A equals F net over m? It tells you that a net force applied to an object causes that object to experience a change in motion. The force causes the object to accelerate. It also tells you that for the same object, if you double the force, you will double the object's acceleration. Lastly, if you apply the same force to objects with different masses, the one with the most mass will have the smallest acceleration, and the one with the least mass will have the greatest acceleration. Get it? Determine how the force exerted on an object must be changed to reduce the object's acceleration by half. Recall that forces are measured in units called newtons. Because F net equals ma, a newton has the units of mass times the units of acceleration. So 1 newton is equal to 1 kilogram meters per second squared. To get an approximate idea of the size of 1 newton, think about the downward force you feel when you hold an apple in your hand. The force exerted by the apple on your hand is approximately 1 newton. Table 1 shows the magnitudes of some other common forces. Figure 6. Changing an object's mass affects that object's acceleration. Compare the acceleration of one cart to the acceleration of two carts for an applied force of 1 Newton.
Okay, so before, when we were trying to find the slope, we were doing rise over run, right? You pick two numbers, find out what your rise and your run is, that gives you the slope. Do you remember that? The only thing that they're talking about here is that your slope's going to be different according to how many cars you have added on. Now, this should make sense to you. If you were trying to push your bicycle up a hill, it's a whole lot easier to push the bicycle up the hill instead of your golf cart, right? Because it has more mass, which requires more force. Also, the next thing I would like you to do is I would like you to write this down. FMA, right? So our force in this class is going to be watt units. Newtons, thank you. What's our mass going to be? Kilograms. What is going to be our acceleration? Meters per second squared. When we start going into, which we're going to start going into the first 3 laws of Newton's laws, right? And when we're doing those, FMA is very important. Okay, and we're going to talk about which one of those rules it applies to, but it applies to the second law of motion. F equals ma. Okay, and we can use that formula for whatever we're looking for. If we're reading the equation or the word problem, and you see the letter N, you know that's force, right, guys? If you see something like kilograms or grams, you know that has to do with mass. When you see something that says A, you know that is acceleration, and that is meters per second squared. Is everybody good so far? Is there anything else that you thought that was important on this page that you should have wrote? I don't think so. So let's go to the next page, please.
Newton's second law. Figure 7 shows 2 dogs pulling a sled. Each dog pulls with a force of 40 newtons. From the cart and spring scale investigations, you know that the sled accelerates as a result of the unbalanced force acting it. Would the acceleration change if instead of 2 dogs each exerting a 40 newtons force, there was one bigger, stronger dog exerting a single 80 newtons force on the sled? When considering forces and acceleration, it is important to find the sum of all forces, called the net force, acting on a system. Newton's second law states that the acceleration of an object is proportional to the net force and inversely proportional to the mass of the object being accelerated. This law is based on the observations of how forces affect masses and is represented by the following equation. Newton's second law. The acceleration of an object is equal to the sum of the forces acting on the object divided by the mass of the object. A equals F net over m. Solving problems using Newton's second law. One of the most important steps in correctly applying Newton's second law is determining the net force acting on the system. Often more than one force acts on a system, so you must add the force vectors to determine the net force. Draw a free body diagram showing the direction and relative strength of each force acting on the system. Then, add the force vectors to find the net force. Next, use Newton's second law to calculate the acceleration. Finally, if necessary, you can use your knowledge of accelerated motion to find the velocity or position of the system. Figure 7. The net force acting on an object is the vector sum of all the forces acting on that object.
Okay, so when we're talking about vectors, all right, if the vectors are going in the same direction, what do we do with those vectors? Add them together. Okay? If the vectors are going in opposite directions, what do we do? Subtract. Everybody good so far? Okay, so let's look at the practice problem on the bottom of that page. Are we ready? We got this. Come on. So it says two horizontal forces, 225 newtons and 165 newtons are exerted on a canoe. What is the forces applied in the same direction? Find the net horizontal force of the canoe. So what are we going to draw here? Okay, so let's draw the canoe.
Would the horizontal forces be to keep the size?
So I guess we could say it that way, or we can just say there's some ropes that are applying. So based on the information, how are these forces going? Are they going in the same direction, or are they going in opposite directions?
That they're exerted on.
Okay.
They're applied in the same direction.
Okay, so let's go ahead and do that.
So you're gonna add.
My canoe is my system. I'm going to put my dot there, right? It says there's two forces applied, correct? Okay. So what is my first force applied? What's the number? 225 newtons. What's my second force? 165. What do you think we're going to do with those two? Add them together. So what is my total?
390.
Okay, 390. So what is my net force? What is my net force? My net force is in that direction, right? How many newtons? 390. That's all we got to do. I drew my free body diagram. I showed my two vectors, and I added them together, and it came up with that number. Is everybody good so far? That one's fairly easy, isn't it? Let's go ahead and do the second problem.
We did this on this Friday.
Mhm.
So can we have questions like number 6?
Sure. If the same two forces are in the previous problem are exerted on the canoe in the opposite directions. So now what I'm going to do is I'm going to say, all right, so in this free body diagram, I'm going to have them in opposite directions. Everybody good? Now, I'm going to say 225 is this way and 165 is that way. All right? What do I do with these forces? Subtract. If I subtract them, what number do I have? It's got a calculator on the desk.
Oh, it's called. I forgot.
60.
Okay? 60 newtons going in that direction is my force net. You feel good so far? Drew the picture, identified the system, drew my vectors, and then I came up with a solution. Everybody good? Let's go ahead and let's go on to the sample problem 1. Are you there? Sample problem 1 on page 97. 9, 10, and 11. So where we're going to stop here is we're going to stop here. Those of you that are in the lab station first, what you're going to do, praise God, you're going to go back there, and what you're going to do is open up your computer, and you're going to see a Nearpod for forces. Okay? So get up and go. Those go first. Same people go first every day, and they change during the week. So last week, did we not go to the lab yesterday? We wasn't here in the lab. We wasn't here yesterday. We didn't go to the lab yesterday. Fantastic. Okay, so let's do it this way. This will be easy. People in the back 2 sections, back 2 tables, go to the lab tables. Those in the front 2, y'all can stay here first. Yeah, in there. Okay, my students that are up here, what we're going to do is we're going to do the sample problems. Are you ready? Okay, so if we look at our sample problems, we're going to do question number 9. Question number 9 says a spring scale used to exert a net force of 27 newtons on a cart. The cart mass is 0.64 kilograms. What is the car's acceleration? Now, guess what we're going to be using? This beautiful triangle. Okay? So the first thing you want to do is you will want to put in your variables, okay? F net, mass, and acceleration. Everybody good so far?
Okay, hold on.
Just wait. Okay, spring scale is used to exert 2.7 newtons. All right? Where does newtons at? Right there, right? So that's 2.7 newtons. Okay? The next thing it says is that the car's mass is 0.64 kilometers. Where's 64 at? Okay? And what is it looking for? Acceleration, correct? Okay. Are you ready? It's going to be easy. Force net, mass. We're looking for acceleration, right? We put our hand over acceleration. What's our formula? F net over m, right? F net over m is our equation. So we're going to do 2.7 newtons divided by 0.64 kilograms. So in your calculator, put that in. And write down your acceleration. Now, the question is this. What is my units of measurement here? Okay. We're looking for A, meters per second squared, right? So write that down. Everybody good? I'm going to let you do the next problem. Yes, ma'am, I did. 4.2 meters per second squared. That's question number 9, right? That's where we're at. Now let's go to question number 10. Is everybody ready? All right, so let's see what we got. Number 10 says, this person is learning how to ice skate. She wants her mother to pull her along so she accelerates at 0.80 meters per second, and her mass is 27.2. What is the force? Okay? Meters per second is what? Acceleration. So let's put 0.80 meters per second squared. All right? What's 27.2 kilograms? Okay? So that's 27.2 kilograms. What are we looking for? Force net. So, cover what you're looking for. I am going to take my mass and I'm going to time my acceleration. This is divide. This is time. You got it? So for force net, that is mass times acceleration. So I'm going to do 27.2 kilograms times 80 meters per second squared. So let's multiply this. Kristen, what'd you get? What did you get?
Oh, so we don't got to split it?
There's no squared at all. So here, Haley, it's okay, because listen, this is very confusing. This meters per second squared is a unit of measurement, kind of like pounds. Okay? So what did you get, Kristen?
2.17.
Change it out of scientific notation. Go back to your mode. Change it to normal. Make sure it's in radian. Every day y'all come in here, y'all got to do that with your calculator because you're going to have scientific and you're going to have degree. What you got?
Now it says 21.76.
Thank you. So what am I going to say? Can we say 22? Right. Is yours in degree? In scientific notation. Check your mode. You need to have it in normal, in radian. And then just do second answer and you should be able to see it.
So are you asking me, can we round?
Yeah, that's what I'm asking. Can I round to 22?
Yes.
Okay? And that is what units? Newtons. Very good. Y'all good so far? Fantastic. All right. So let's see what it says for our challenge. Are we ready for a challenge, or do we want to skip and go to the next page? Okay, she wants to skip and go to the next page. So far, what we have learned is this is Newton's second law, correct? So what do you remember about Newton's first law? What did you remember about Newton's first law?
We learned that yesterday.
Nope. You learned that back in 9th grade.
Oh.
Okay? Here's an example of Newton's first law. An object is at rest unless acted upon by an outside force. Okay? You got it? So let's write this down. Newton's first law. Yeah. Google. Object at rest will stay at rest unless acted upon by an outside force. Everybody good so far? Okay. Can we think of an example that we could show for Newton's first law? Well, for Newton's first law, say I have a table and I have a book on that table. Okay? My force diagram, if I was just doing the book by itself, correct? I would have force normal on the book by the earth, gravity, force normal on the book by the table, right? Now, what would happen to that book if I came and took my hand and pushed the book? What would my force diagram look like then? Well, I would have force gravity on the book by the earth, and I would have force normal on the book by the table. But now I have a third one. What is that one? Force applied. Force applied on the book by my hand. My net force here is equal to 0, right? My net force here would be what? This direction. Newton's first law. Is everybody good? Okay. So let's go ahead and turn to page, please. To section 2. Section 2 is what we're supposed to be doing today. So what I'm going to do is we're going to play that. You're going to take some notes. and then we're going to rotate to the back. Okay, everyone? Does everybody have this so far? And I'm sorry it's so long today. It's just we're trying to catch up. It was slow yesterday. Be right there.
When the net force acting on it is zero? Newton's second law says that if F net equals zero, then acceleration equals zero. Recall that if acceleration equals zero, then velocity does not change. Thus, a stationary object with no net force acting on it will remain at rest. What about a moving object, such as a ball rolling on a surface? How long will the ball continue to roll? It will depend on the surface. If the ball is rolled on a thick carpet that exerts a force on the ball, it will come to rest quickly. If it is rolled on a hard, smooth surface that exerts very little force, such as a bowling alley, the ball will roll for a long time with little change in velocity. Galileo did many experiments, and he concluded that if he could remove all forces opposing motion, horizontal motion would never stop. Galileo was the first to recognize that the general principles of motion could be found by extrapolating experimental results to an ideal case. In the absence of a net force, the velocity of the moving ball and the lack of motion of the stationary object do not change. Newton recognized this and generalized Galileo's results into a single statement. Newton's statement: an object that is at rest will remain at rest, and an object that is moving will continue to move in a straight line with constant speed if and only if the net force acting on that object is zero, is called Newton's first law. Inertia. Newton's first law is sometimes called the law of inertia because inertia is the tendency of an object to resist changes in velocity. The car and the red block in Figure 8 demonstrate the law of inertia. In the left panel, both objects are moving to the right. In the right panel, the wooden box applies a force to the car, causing it to stop. The red block does not experience the force applied by the wooden box. It continues to move to the right with the same velocity as in the left panel. Is inertia a force? No. Forces are results of interactions between two objects. They are not properties of single objects, so inertia cannot be a force. Remember that because velocity includes both the speed and direction of motion, a net force is required to change either the speed or the direction of motion. If the net force is zero, Newton's first law means the object will continue with the same speed and direction. Figure 8. The car and the block approach the wooden box at the same speed. After the collision, the block continues on with the same horizontal speed.
Okay, so if you look here, you wrote down the definition I gave you for first law, correct? The other thing that I want you to make sure that you write down is the word inertia. Inertia and the first law go hand in hand. Okay? Just like the second law with force, mass, and acceleration, the same thing with inertia.
Vocabulary. Science use versus common use. Equilibrium. Science usage. The condition in which the net force on an object is zero. When an object is in equilibrium, the object's velocity will be constant. Common usage. A state of balance. The pollution disturbed the ecosystem's equilibrium. Equilibrium. According to Newton's first law, a net force causes the velocity of an object to change. If the net force on an object is zero, then the object is in equilibrium. An object is in equilibrium if it is moving at a constant velocity. Note that being at rest is simply a special case of the state of constant velocity, v equals zero. Newton's first law identifies a net force as something that disturbs a state of equilibrium. Thus, if there is no net force acting on the object, then the object does not experience a change in speed or direction and is in equilibrium. As figure 9 indicates, at least in terms of net forces, there is no difference between sitting in a chair and falling at a constant velocity while skydiving. Velocity isn't changing, so the net force is zero.
Okay.
When analyzing forces in motion, it is important to keep in mind that the real world is full of forces that resist motion, called frictional forces. Newton's ideal friction-free world is not easy to obtain. If you analyze the situation and find...
All right, so what is a good drawing for equilibrium? What would be a good drawing for equilibrium? Well, let's see, a scale with both of them being balanced, right? Equilibrium is where you have the net force of 0. Thank you very much, ma'am. All right, next page. Got one more page, we'll be done. You need to go in the back. Now, how do you think weight affects this?
Like with the car, when it was going up the thing and they had to pull it, the weight of it changed how much force.
Right. What law reference weight? The second, right? Force, mass, and acceleration. If the mass goes up, what happens to the acceleration? If you're going downhill, it's going to go really fast. If you're going uphill, what happens? Slows down because it's more force you have to apply. Does that make sense to you? Okay. So on this page, I'm not going to read it to you, but under weight and gravitational fields, when we're talking about gravitational fields, what are we talking about? We're talking about, remember how you did magnets and how things were attracted and repelled from each other? That's what it's talking about there, okay? So we're going to go ahead and skip that. Is there anything else on this page you think you need to write down? Everybody good? I'm good. Let's go ahead and go to the next page. We have math problems, but we are not going to do them today. We will come back. How about the next page? Apparent weight and weightlessness. What is the difference between those? What is apparent weight? Scale. When you step on a scale, that's your apparent weight, right? Right? So write apparent weight equals scale. What is weightlessness? When you're in space, right? You have no gravity at all pulling you down. That's considered weightless. Are you good so far? Okay. I've got a couple more minutes. We have problems we're going to do tomorrow. And then what is a drag force? Well, it says here, a drag force is a force exerted by a fluid on an object opposing motion through the fluid. So, have you ever seen where viscosity, you know what viscosity is? Viscosity is the motor oil that you put in your car and how thick it is. Okay? If you had a tube of motor oil, this is a 10 weight, this is a 20 weight, and you had the same size of steel ball going through, which one do you think would be slower? 10 is very, very thin. Thicker the weight, the higher the number. So with this one goes slower than water, but this would go faster. I mean, then faster than this, right? So if you had three things, you had one where you had water, you had one with 10 weight and another one with 20 weight. This would go the fastest, this would be the second, and this would be the third. And that's all they're talking about. Any questions? So when you go back to the back, what you're going to do is you're going to draw a line on your sheet, and you're going to go and you're going to open the Nearpod up. Do not spend a long time going through the Nearpod looking at the articles or anything like that. Go through, answer the questions, and if there's something else that we haven't covered today, write it on your paper. Guys in the back, go ahead and get ready to come on over here. Make sure you wipe your station. Ladies in the front, take your book with you. Your book goes at the end of your lab station because you don't need it the rest of the day, and then sit down and do your Nearpod. Please make sure you're across from each other, okay? Those of you that are online, the next thing that you would want to do is you would want to go and do the Nearpod, which if I can show you really quick. If you go to our class, under classwork. Sorry, Kristen. You would go to today's assignment. And then what you're going to do is you're going to hit the Nearpod. Now, when you get to the Nearpod, what you're going to do is you're going to use your Google account, okay? Once you do your Google account, it'll already tell you it's you. What you're going to do is go through that and then write down anything that you don't know. So right here, grab my name from Google. And then you would have to sign in if you need to, or you just say who you are. All right, guys? So that's all that you need to do. You need to do that also. Make sure you turn in everything by midnight tonight. Have a good day.